In example 19.8, we're going to be continuing to look at the concept of transformations as it applies to different log functions. But here we're not being asked to graph anything. It says here, describe the transformations given by each equation and determine the largest possible domain and range. So we have essentially three things to do here. Describe the transformations, figure out what the largest domain would be, and also talk about the range. So to help with this, I'm going to make a sketch. This does not have to be the most amazing graph of a log function that you've ever made, but you do need to be familiar with what the basic shape should look like. So when I look at h of x, I see h of x is equal to 2 plus log base 2 of x. Now for starters, I'm going to rewrite this so that way it says log base 2 of x, and then I'll put plus 2 here at the end. The logarithm that I am dealing with here is a logarithmic growth. So there is a particular shape associated with that. The shape is going to be increasing, going from left to right, and it looks something like this. Again, it's just a crude sketch, doesn't have to be anything fantastic, and I'll identify also that there is the vertical asymptote there on top of the y-axis. What now I need to think about is how does h of x compare to this basic parent function? So this is just the basic parent function for an exponential growth. And what I see is that plus 2 means that I should have to shift up by 2. So if I take this picture of the parent function and I shift it up by 2, it's going to look maybe something like this. This is what h is going to look like. Now, by shifting it up by 2, that does not change the location of the vertical asymptote. It's still located at x equals 0, which means the domain should also still be from 0 to infinity, which is the standard domain for our log functions. And then the range still has an arrow pointing down, still has an arrow going up to the right, so you're still going to cover the entire spectrum of values for the range. So your range is still going to be all real numbers as well. So the domain and range conversation there is done. The transformation conversation is also done, and I'll just write it up nicely here. I'll use capital T for transformation, and I will say vertical shift up by 2. And that takes care of h of x. Let's do the same thing for part B. We have g of x is equal to -1 times the log base 3 of x. So again, I want to think about what transformation is being applied to what type of logarithm. This is log base 3, which is going to also be an example of growth. So I should be able to get away with using the same parent function picture that I did for part A. But now I need to recognize what's going to be happening with the -1 multiplier. So for the transformation, this is going to result in a reflection, specifically a reflection over the x-axis. And that is the only transformation that I have. So from here, I need to investigate what's going to be the domain and what is going to be the range for g. So looking back at my parent function picture over here, this is my standard parent function picture for growth. And it doesn't matter what the base is. If it's growth, this is the basic shape. If I reflect this thing over the x-axis, then let me pick a different color here. Let's go with this green color. If I reflect it over the x-axis, it's going to look something like this. This is going to be the graph of g. Now when I do that, my vertical asymptote doesn't change. The arrow on the left side is going up along the vertical asymptote. My arrow on the right side is going down and to the right. So I'm still covering the entire spectrum of real numbers for the range. I don't see any reason why the domain and range need to change here. So the domain is still going to be 0 to infinity, and the range is still going to be all real numbers. So there's our analysis for part B. And then finally for part C, we're looking at f of x equals log base 1/2 of negative x minus 2. So there is two transformations going on here, one of which is because of the -1 multiplier with the x, and the other is because of the -2 here at the end of the statement. So as far as the transformations are concerned, I'm going to have to list those as two steps. And when we talked about transformations in section 4, and every time since then, we have emphasized that there is a proper order of applying the transformations. So anything that is multiplier driven needs to be a high priority transformation, top of the list. That's going to be that multiplier of -1, which is created because of a reflection. So you're going to have a reflection this time over the y-axis, and then you will also have a vertical shift, and this will be a vertical shift down by 2. But if I take away the multiplier and the subtraction of 2, if I just cross those out, then my parent function is going to be log base 1/2 of x. We're talking about a decay function now, not a growth function. I want to give a picture of this so we understand what's going to be happening transformation-wise. My generic decay function for logarithm looks like this. Vertical asymptote still right on top of the y-axis. That's our decay parent function. I have to do two things to this. I have to first reflect it over the y-axis. When I do that, my vertical asymptote doesn't change, but my graph is now on the other side of the vertical asymptote. Then I'm supposed to shift the whole thing down by 2. So when I shift the picture down by 2, it's going to look something like that. And that is approximately what f is going to look like. So my domain, although the vertical asymptote did not move, is not going to be 0 to infinity. The domain for f is now going to be -infinity to 0, but the range is still going to be headed in the positive infinity and negative infinity directions with the arrows that are at the ends. So the range is still going to be all real numbers, although the domain is not going to remain the same. So we have our two transformations, and we have our domain and range. This completes example 19.8.